Okay, welcome to Saturday Morning Tonic, where we're going through the answers for this week's geometry questions. And this covers polygons, parallel lines, and circle theorems. I know circle theorems are definitely things people don't like, so hopefully this gives you a little bit more work with them and hopefully see them in a real life situation. If you've seen this beforehand, you'll see there's a bonus challenge from Professor Ross Atkins from the University of Canterbury. A little problem. I haven't actually had any emails with solutions yet, so that is still open. If you want, there'll be a prize for the first full solution to me. And don't forget, if you want these questions ahead of time, join our Patreon team. We have over there all the resources from previous. You can see a collection of questions from the past, and you can even find full solutions rather than looking through on the live streams. So save yourself some time. There's 54 days to go. That's going down real quick. I remember we started above 80, so hopefully that's starting to kick in and is a good motivation for some out there. Let's get started. So a quadrilateral four-sided shape has the angles 2h plus 50, 30 plus 3h, 4h plus 10, and 5h subtract 10. Find the value of h and what's the name of this shape. So in polygons, we know that, I'll do it properly here, that we know that in general, a polygon has the internal angles according to the formula n subtract 2 times 180. And this is useful for all sorts of polygon problems. And even though we should know as a fact that the internals of a square or a four-sided shape are 360, it still proves that this formula works. So n being the number of sides, that's 4 subtract 2. And so we have 2 times 180, which is 360 degrees. That's just, part and parcel of showing off our working out if you want to be extra thorough, but you could just jump straight to the 360. All of these angles are just ways of expressing numbers. So if I had 50, I could write that as 2h plus 10, and in this regard, h would be 20, because 2 times 20 plus 10 is 50. So you can think of those as four things that need to be added together. 2h plus 50 plus 30 plus 3h plus 4h, etc. Saying them all out loud. We know that if we did add them all together, it will equal 360 because that's the total. Want a bit of clearing up here, a bit of simplification. And the best way of doing that is highlight. You can circle if you don't have highlighter access in the exam, of course, because you've got to use just pen. And this just hopefully ensures we don't miss anything. So 5h, 9h, 14h. I keep writing in that. I thought I changed it, but I just changed the color. 14h, and all of those numbers we've got 50 plus 30, 80, 90, take away 10, 80. Okay, once we've tidied it up, we go back to the skill of solving linear equations. And this is an absolute privilege. It's a treat to be able to solve a simple linear equation in a higher paper because they're typically quadratic. So in this case, write that down if you're not sure how to proceed. It's linear equations. We're going to subtract 80 from both sides. So we get 14h equals 280. And then we know that 14 goes into 28 twice. So really weird. Maybe it's my subconscious at work, but earlier I said h was 20, and so it is. Now, what is the name of a shape if h stands for 20? We first of all have to look at all of these and find out what they were in real terms. So 20 times 2 is 40 plus, that's 90 degrees. 60 plus 90. Okay, so we've got a four-sided shape with two 90-degree angles. We could have a rectangle. We could have a trapezium at this point. Let's have a look. 80 plus, there's another 90. And 100 take away 10, that's another 90. So once we know h is 20, all of those are 90. What sort of shape are we looking at here? Well, it's a rectangle. And here's a question for you, because some people say, well, it could be a square. Is a square a type of rectangle, or is a rectangle a type of square? That was thinking time. In fact, a square is a special type of rectangle. A rectangle is defined by a four-sided shape with four right angles, two pairs of parallel sides. There's a very special case where all of those sides or edges are exactly the same. So we're going to class this as a rectangle, and we won't be wrong. Okay, using the mouse, 1 second. The number 4 is to be cut into a piece of wood using a circular cutting saw in an italic font, naturally. The wood will slide horizontally across the board and make parallel cuts BA to CD. The cutting table is then turned by an angle of 50 degrees anti-clockwise, and it's going to cut then BE. And if points AD and E are collinear and FD equals FE, find angle BAD. So there's a few bits of information on there that make this a little bit easier to deal with, and we're going to have to add them on. And here's my funny old-fashioned shape recognizer tool. Oh my goodness, it worked first time. Those that have seen previous, oh look, now it won't enjoy that. Those that have seen previous live streams will know that this tool likes to latch on to different points, but that'll do us. That'll do indeed. And that's the collinear. So collinear means that they're all on the same line, straight line. And if you think for a moment, 3 points not always necessarily forming a straight line. So that's unique, and that means we can draw that line and it creates triangles. This sign and this sign means that they're parallel. That's where we make the first, oh, better not do that. That's where we make the first two cuts. And then we have the fact that FD equals FE. So we can draw a line here and a line here. The crucial point, and let's highlight what we've done as we go along, that this is true and collinear. The crucial point is this: the cutting table is then turned by an angle of 50 degrees anti-clockwise to cut BE. So if we're cutting in this direction, and this is, I guess we could draw the saw, looks like this, and it's cutting in that direction, and it's on a board like this, and then the board is moved anti-clockwise 50 degrees, then what does that imply about the angles here? Well, it's this, isn't it? That we're going to have turned that there. And so now we've got BE being cut where previously BA was cut. So this is our 50 degrees, and that's our way into this problem. And the fact that this triangle is isosceles. Isosceles have a very interesting property. I'm kind of going over this stuff. I'm not here to just give answers. I'm trying to give a little bit of background if you're missing something. So a quick background on isosceles: if you have something like this, these two angles are equal. And so generally, if you know this angle, in fact, if you know any one of the angles, you can work out the other two. Special triangle, if we know that this is 50, and they all add up to 180, we can very quickly write down that we're dealing with 130 shared equally between two angles. So 130 over 2, 65. Let's get rid of that and add it to our diagram. So 65 and it implies this is also 65. What else can we do? We've got everything on, except we want to focus on angle BAD. Where is that? Well, typically the angle is the middle one where the angle lies. So we trace B to A to D, and it's this here. Now there's a reason, like we can go a couple of ways about this. So from this point onwards, it depends on what knowledge you have. But if these two lines are parallel, we can extend them, and this line cuts across those parallel lines, and so we have this angle here, 65, is going to be equal to this angle here, which is 65. There's another way of getting to that point, but there's quite an elegant way to save some time. Now with parallel lines you have alternate angles, complementary angles, and supplementary, and so this would be complementary. We have those well, some people call them F angles, but you can't really put that in the exam. These are equal. There we go. Angle BAD is 65. Let's have a little look. Nope, that's it for that page. Excellent. Told you this week would be a short one. Some of them have taken a long time. Hey, this is very strange, and I think you probably felt the same when you saw this diagram. There are questions like this. They rely on understanding of the internal angles of polygons, but this one looks very off-putting. Where does the pentagon start and when does the hexagon end? So a regular pentagon and hexagon overlap as shown. Find angle H. I think you find when you start the question it's not as bad as all that. But let's look at our formula from earlier. N take away 2 multiplied by 180. So we're going to start with the hexagon. Why not? And therefore that's going to be 6-sided. So 4 times 180. And you would get 720. Now the 720 is the total, but since it's regular, remember what that means? Regular means that all of those angles are the same. So we divide it by 6, and we get each internal angle of 120 degrees. Not sure why that's times. Let's put an equal sign there. Maybe we would put a little internal. That's good. So now we're going to look at the pentagon. So we'd pent n minus 2 again times 100. I wouldn't be worried about the amount of times that you write that formula, because the more you write it, the better you're going to remember it. 5 take away 2 this time, which is 3 times 180, and that's 540. Let's go back and put degrees. And then 540 divided by 5 is 108. Just to confirm. I'm writing it backwards because sometimes it doesn't register properly and I have to do the second letter first, or the number. So that's an internal for the pentagon. Now you might still wonder how that even helps, because this angle we're after is not part of either of those. For example, we know this whole length here is one of the, or is it? No, this one. This whole length here is the hexagon internal. And then focusing on that, now this is the pentagon internal. Where does one start? Where does one end? Maybe if we knew this whole thing, we could take away part of it, but it's a long thing going on there. Essentially, times like this, you write on the diagram what you know so far, as much as you can, and hopefully something clicks. So focusing on the hexagon, it might help to visualize it like this. We can see that this is 120. And so is this. This whole area we're going to stay clear of because it's a mess. But where there's a clear angle, now here's a clear one, and it's inside that shape with H. Here's another one. Really good. H is left though, so that's, don't worry about that yet. Wouldn't it be nice to know this one and this one? And you've probably seen it already by now. Those are the internals of the pentagon. Sometimes visualizing it is the tricky part. Like so. And we found that those were 108. Now I know the focus of this question has been on regular polygons. And those regular polygons give us nice numbers to work with. But it's still true that any five-sided shape is going to have a total of 540, no matter if they're all equal angles or not. And you can see the shape that H resides in has 1, 2, 3, 4, 5 sides. So it will have a total of 540 like its regular pentagon. And so we could just see what we have so far. We've got 108 times 2 and added to 120 times 2 gives us, wait, I'm not sure that's correct. I'm going to do that again. 108 times 2 plus 120 times 2. Oh, well, it is. Never mind. Don't sometimes doubt the numbers because they look too weird. If we add all those up, we've got 456. 456. And we're going to subtract that from 540 to see what is left. 540, subtract answer, 84. So angle H equals 84 degrees. Love that question. In fact, do we do all of them on there? Thankingly. We found one, the last one already. Beautiful, but it is a big one. Yeah, it's one of those ones. Okay. Below is the plan view of a square garden ABCD. BE and BG are electricity cables that run underground, tangent to the circular pond with a center H. So, straight lines, tangents, circle theorems. Probably thinking that. A bridge features that goes across the middle. So, if it wasn't clear in the diagram, it goes from here to here, which essentially you can walk across. And let's go back to pen. FHI is 3 times the size of FBI. Find FBI. All right. This is our chance to use a little bit of algebra. Because you might be looking at this straight away and it's fair enough. You could probably think, well, I've got some right angles here. Maybe that's going to help one day. Not so much. I mean, it does make this a right angled triangle, but you don't have this side, this side. It's all a bit of a mess. But the key is on the final statement here. The FHI is 3 times the size of FBI. How else can we write that? Well, let's just say if FHI, maybe just do FBI, let's call it X. Then FHI here is 3x. Where does this reside in? It resides inside a 4-sided shape. Now, if you know anything about tangents, the one probably you might call it the most easy and first circle theorem, you know that where this tangent touches the edge of the circle and then goes through to the radius, it will always touch at 90 degrees to the radius. So we actually know a bit more about this shape than meets the eye initially. We have the total of 360. We talked about this earlier. The total in a 4-sided shape is 360. We have 2 known angles of 90, so that's 180. And what we're left with is 4x. So if we took away the 180, we'd be left with the 4x. There's a number of ways I could have set this up, but I'll set it up this way. I could have said 180 plus 4x equals 360, but I've done it this way. So 180, therefore, equals 4x. Wow, okay. Maybe that was easier than at first thought. We divide both sides by 4 and we get that one of those x's is 45. Okay, cool. So we're going to add that to our diagram. 90, 135 degrees. Okay, here we are. And moving on. A triangular canopy is planned to be constructed above the pond with vertices at points J, F, and I. So that was at 24. Let's try the smallest. So J, F. Let's do J to F. Oh, what? I didn't think F was added on. How strange. Maybe I did create it in here. Okay, well, we could do this. It's probably not worth using this automatic drawer. Spent a while doing this. Let's try and do it carefully. So F to J, like this. And where else? F and I. And it's going to cut through there, so let's make that smaller. Oh, there we go. Not too bad. I think we'll cope. If you're doing this on paper, you're going to have a better time of it than I am. You can use a ruler, for example. So this is essentially the canopy that's going to cover the walkway. And we want to find angle FJI, but we don't ask questions why. We just need to. There it is, FJI. First step is knowing what you're trying to find. Now, if you know anything about your circle theorems, I will just see if I can draw a mini diagram here. We know that if a tangent touches the circle at this point, and then a triangle comes from here to touch all of those circumference, essentially, then the angle created with the tangent and the circle at the triangle edge is the same inside the triangle on the opposite side. Can you see that in the diagram? Essentially, okay, I can't rub that one out without rubbing anything else out. But essentially, we have a triangle that, let's just do it here, that starts here and meets the tangent at here. So this angle is of importance. And if we turn this into a right triangle, we could figure out exactly what those angles are. Alternatively, we can look at this as isosceles. I think that might be the better way, rather than a right triangle at this stage. So I've seen a quicker way. Let's get that back to the right. Zoom. If this whole triangle was to be examined, oh gosh. There we go. That's better. If the whole triangle was to be examined, we have 45, let's draw it again, 45 degrees at the top. Therefore, it's being isosceles, what we saw earlier, we can split what's remaining into two. So 180 take away 45 is 135. And that leaves us with 67.5 degrees for this angle and this angle. And they just so happen to be important to us. So 67.5 degrees is the angle made between the tangent and the triangle that's inside the circle. And therefore, the angle opposite that inside the triangle is also 67.5 degrees. Also known as the alternate segment theorem in circle theorems. We're flying. I would recommend drawing a diagram as big as you can. It's worthwhile talking at this point because looking at my diagram, it's getting pretty crowded, and there's another part to the question. The area of the circular pond is this. It's not too big. A straight path is to be added from B directly to the pond edge. Find the shortest distance from B to the edge of the pond, given your answer correct to 2dp. Okay. Let's identify it first. So from B, we go straight to the edge of the pond, and it looks like it's there. If we carried on, that entire length could be useful to us. Because if you imagine that entire length with the tangent, you actually have a right triangle. But let's look at this bit by bit. The dotted line is also the radius of that circle. We know the radius because we know the area of the pond. So this is reverse engineering the circle equation that we saw in a previous live stream. Pi r squared sounds like area to me. And if you know the video, you know the video. 3.8013. And all we have to do now is rearrange because pi is a constant. And we can re-engineer. So if I divide by pi, like so, and then I square root, put that in a calculator and you'll find that it's 1.0999. And I always recommend writing as many decimal places as you can manage, because otherwise you'll have to type that in a calculator again to get the full accuracy. Now what do we have here? We've got now the radius, which is cool. That means the dotted part. But you'll note that the radius is also h to I. So if we draw that triangle that goes down from B, and do we have a point at the center? Yeah, H here. Wow, anomaly. H, and then out to the, don't like that, do it again. There we go, out to the tangent. We've just found out, let's call it I. We've just found out that this is 1.09, and I'm going to put dot, 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 because it's going to continue, and whenever I want the calculator, or we're only going to calculate, I'm going to go back to this big value. And what else do we know? We know that this angle up here is half of the 45 degrees that we've just found it to be. So up there it becomes 22.5. And that's trigonometry. So let's call this side that we want to know BH. BH, B to H, or HB pencil. I'm not sure about the zoom. Flick it back to normal. Maybe it's this. I'll carry on. No, one more. Nah, leave it at that. So, trigonometry it is. And what have we got? Well, let's go for orange. Here's the angle, so this is the opposite. And opposite the 90 degrees, we have the hypotenuse. So that looks like sine rule to me. That looks like sine ratio. So sine of the angle, 22.5, is equal to the opposite, 1.09 dot, 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 over what we want, which is x. There's a neat little trick where you have these sort of equations, and you can do them in two steps if you want, you know, times both sides by x and then divide by sine 22.5. But you get used to seeing that these two just switch around. So in this case, x equals 1.09 dot, 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 divided by sine 22.5. And we're going to put that in a calculator now, and we get that total length is 2.874428.273 blah 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 meters. Could be useful so we don't forget to do the meters at the end. What was our aim here? The shortest distance. So if we look at the line, essentially drawing the circle across here, we wanted to find this distance here. We know that BH is equal to 2.87, etc. And we want B to X. No, that's not X, is it? We didn't call that X. We didn't call it anything, I don't think. We'll just call it, what letter haven't we used? Maybe R. We'll call it B to R is equal to BH subtract the radius, and BR represents the shortest distance from B to the circle, so we could just do a takeaway sum of 2.874 etc. using the proper big number up here, and subtract the 1.09 etc. radius to leave us with 1.774432.196 meters. Is that what we wanted? Yep, the direct from that point to B. That was really cool. Look how much maths we used, how many different areas of maths. Although it's a circle theorem question, you've got all sorts going on. And only stuff we've done previously, mind. Give your answer correct to 2 decimal places. That's not worth losing a mark for, is it? 1.77 meters. And we was right at the end what that decimal place was. I think that's it for this week. We've covered a good few topics. Certainly topics that come up a lot. I would bet all of them do. So keep practicing these ones, and let me know in the comments if you want any more practice questions like this, or for me to go through any particular one. And I've come back to the start here. Don't forget to do this bonus challenge. It's amazing. It took me about 8 minutes to do it, so not an easy question. And don't be put off if it takes you 20 minutes, an hour, or a day. It's definitely very satisfying. Anyway, take care, everyone. Oh, hold on. I was about to end live stream. I think I'm pretty used to not seeing any comments. But hello, Maths Explained in the comments. I don't have a timestamp as to what was a nice question, but that's cool. Alpha geometry? Not sure. Not think I do. If you're still around, I'm not sure. But sorry I missed it. I think I probably used to not see anyone. Thanks for coming by. Message me off live stream if we could talk about alpha geometry. Sounds interesting. Anyway, everyone, thanks for watching. And if you're not watching live, nice to see you, and hope you enjoyed the questions.